From the far north, they heard a low wail of the wind. Uncle Henry stood up. "There's a cyclone coming, Em," he called to his wife. "Quick, Dorothy," she screamed. "Run for the cellar." Then a strange thing happened. The house whirled around 2 or 3 times and rose slowly through the air. Dorothy felt as if she was going up in a balloon.
So the goal of this project is to understand the effects of intense thunderstorms on the stratosphere.
So we think of these thunderstorms, big thunderstorms, as being chimneys from the surface up to the upper troposphere and the lower stratosphere. So how much air is going up? What's in that air that's going up?
So NASA does many airborne sciences campaigns primarily to go and answer focused science questions, in particular those science questions that our satellites gives us clues into, but they can't answer the complete picture like we really want and need to do as a science community.
We're centered in Kansas because this time of year, Kansas is the center for producing storms that are deep enough to overshoot into the stratosphere.
Sometimes an air mass can bubble upward. It gets hot down at the surface, particularly in a place like Kansas in the summertime. It gets really hot, and that hot air can be moist, also have a lot of water vapor in it. And as that air rises, it condenses and forms clouds and storms. Now, sometimes it is so hot at the surface that that air has a lot of energy in it. It's hot, it's very humid, has a lot of water, and so it can go very high in the atmosphere, and in fact, can reach the stratosphere.
So we're interested in the impacts of the things that these storms carry up into the stratosphere. So one of the most important is water. Water vapor is a very strong greenhouse gas, so it helps warm the surface of the Earth up.
The amount of water vapor that gets up into the lower stratosphere, you wouldn't think it would, but it actually has a fairly strong climate feedback that we really need to quantify well, and it's something that models really do have a difficult time getting well.
One thing I just wanted to say is forecast trajectories that we've been using from Earth last year.
Other chemicals and pollutants that can get carried into the stratosphere by these storms could potentially deplete the stratospheric ozone layer.
So therefore, we make opportunities available to use our aircraft to go and put together experiments to go address those science questions in much more detail than you can with satellite data alone.
So that's what we're here to find out, is what's coming out of the tops of these storms and how much of it.
Where this is really a center base for us to be able to sample storms with, within the reach of the ER-2 aircraft.
"The road to the City of Emeralds is paved with yellow brick," said the witch, "so you cannot miss it. When you get to Oz, do not be afraid of him, but tell him your story and ask him to help you."
So for what we're doing here, we have 12 different instruments on the plane, and there are quite a few instruments that don't just measure one thing, they actually measure many, many different compounds partially.
We can measure water vapor, ozone, carbon dioxide, carbon monoxide, many, many different species that could potentially affect the climate or the chemistry of the stratosphere.
This aircraft is a very special aircraft where you only have one pilot sitting in the aircraft that's wearing a pressure suit, and pretty much all the pilot can do is turn instruments on and off. And the instrument goes to very high altitudes, extreme conditions, very cold temperatures, minus 50, minus 60 degrees Celsius, very low pressures. And for that reason, the instruments, which you can see, look at it in these wing pods, and you can see another instrument sort of below the pilot seat over behind me, these instruments have to operate robotically under extreme conditions. That means they have to operate over a whole range of temperatures and pressures, and they have to produce extremely reliable data, because this data is critical to answering important science questions.
Do you suppose Oz could give me a heart? Why, I guess so, Dorothy answered. The Tin Man returned, so if you will allow me to join your party, I'll also go to the Emerald City and ask Oz to help me.
We are trying to forecast where convection will occur and whether or not it will actually penetrate into the stratosphere, so that we can then forecast where the aircraft should be to sample plumes that, once they're in the stratosphere, of course they're transported and moved, and we need to figure out where those plumes are going to be so that we can actually intercept them with the aircraft.
So once we know where these storms are happening and where the material is going, we designed flight plans for the ER-2 aircraft to fly through that material and sample it and measure the composition with all of the instruments that it's carrying.
So on the day of a flight day, the first thing that happens is the meteorology and trajectory briefing, so that everybody, and especially the flight team, knows the weather conditions. And then we give our flight plan to the ER-2 team to coordinate, let ATC know what our plans are, and then after that we have an all-hands flight briefing where our pilot sits us down, goes over all the maneuvers, and essentially that 3 hours before takeoff is when we have our go, no-go decision.
That's 806, cleared to Smart Regional is filed, and squawk 1116.
So fortunately, when we're flying, we can get information from the instruments radioed down to the ground. We can watch what's coming out of the aircraft and what it's measuring in real time. And we can use that information to adjust the flight path, where they're flying, or the altitudes that they're flying, to try and get the best sampling.
So the forecasting team actually monitors weather conditions all during the flight in case any storms pop up that are unexpected and we need to turn the aircraft back and return to base, or if it's just things that they need to keep an eye out, while they're actually flying.
Any changes that might happen in real time, we communicate to the ground pilot verbally, and then they relay that information to the pilot in the cockpit, so that anything that can be changed can be done in real time, just not done in the actual flight plan. But since, as a flight planner, we're aware of all of the constraints, that's why we are part of the connection between the meteorologists and the ER-2 flight team.
It went way above the clouds, so far that a current of air struck it and carried it many, many miles away. For a day and a night, I traveled through the air, and on the morning of the second day, I awoke and found the balloon floating over a strange and beautiful country.
So water vapor is one of the two main greenhouse gases that keep the Earth warm. The other is carbon dioxide. And normally the stratosphere is very, very dry. But when you have really strong storms, they can carry a lot of water vapor and ice particles into the stratosphere where they evaporate, which adds a lot of water into the stratosphere. So it acts as a greenhouse gas, and it helps warm the surface up.
If it's really moist, that is, there's a lot of water and a lot of clouds above you, that acts as an insulating layer. So these particles and chemicals that are going up there are acting as insulating layers high above the Earth's surface. But the longer they're up there, the more they insulate. The biggest impact is at night. You see the temperatures aren't dropping very far. So you get these warm, humid nights where people can't sleep. That's because of these chemicals and water particles all floating in the upper atmosphere.
Many of these pollutants don't last very long in the troposphere, in the lower part of the atmosphere, but these storms can very rapidly, in the space of minutes to an hour, carry these things all the way up into the stratosphere. So it brings these pollutants, these chemicals, and this water vapor up into the stratosphere, and then the stratospheric winds can distribute that all around the globe.
So there's a lot of stuff that comes up from the surface. There's things like dust. There's also organic molecules. There's sulfur dioxide, comes from coal burning and other processes, plus all these gases down here. Carbon dioxide, nitrous oxide, N2O, methane. All these gases are also going up, plus a lot of man-made gases, and they're all getting vented up into the upper troposphere and lower stratosphere. Now, what do they do when they get there? So understanding the amounts that are getting up there, understanding what they're doing when they get up there, this is really important to know what's going to happen to both our ozone layer and climate in the future.
Can't you give me brains? Asked the Scarecrow. You don't need them. You're learning something every day. A baby has brains, but it doesn't know much. Experience is the only thing that brings knowledge, and the longer you are on Earth, the more experience you're sure to get.
We want to understand the atmosphere. We want to understand the atmosphere so we can better project where it's going. How will things change? Storms become more intense or less intense? Rainfall, droughts, will those change? We want to understand all of these things.
Well, if a system changes, right, and climate change will likely actually change the boundaries. It may change how often you have the thunderstorms, how big they are. Only if the model has the processes in them correctly can we trust that if the environment changes, it'll actually continue to be able to reproduce what we see. So to get models that we trust in to be able to actually forecast risk in the futures resulting from climate change, we need to really be sure that the individual aspects in the model, how things work, are correctly reproduced. And observations are central to this.
We've been very fortunate so far. The plan that we started with has worked really well. We have many flights where we have sampled a lot of outflow material from these storms. So we're seeing very high water vapor, as much as 5 or 10 times what the normal background stratospheric water vapor is. And this is really a new data set. Flights like this have never been attempted before. The next step in the project is the analysis of the data that we've collected here, and that's going to be going on for the next 2 or 3 years at least. People will be using this data for a long time into the future, we hope.
And having said one last goodbye, she clapped the heels of her shoes together 3 times. Instantly, she was whirling through the air so swiftly that all she could see or feel was the wind whistling past her ears.
It's very exciting to be here and be able to do this with the NASA airplane. This is part of NASA's mission to help protect the Earth.
All of NASA's observations, regardless of the area, all of them are key pictures to understanding the climate system. We really do need to understand all those components, because if you have a large question in one area, that will leave large uncertainties in the whole system.
And we never want to sit back as scientists and feel comfortable with that, but want to make sure we always push the frontier, that we can really ensure we have the best possible understanding and reliability of the system, which matters for climate change, it matters for human health, for so many other aspects.
So we scientists are here to collect, to understand, collect information, and provide that information to both policymakers and people in general.
We're laying the baseline here for research that will go on into the future.
Aunt Em had just come out of the house when she looked up and saw Dorothy running toward her. "My darling child," she cried, "where in the world did you come from?" "From the land of Oz," said Dorothy gravely.